Let us see this problem. We are given a binary tree. We need to print top view of this binary tree. So we draw vertical lines in this binary tree, and whatever comes first in this vertical line, in every vertical line has to be printed. Now here if you see, if I'm drawing the vertical line, although these nodes should come in the vertical line, but pictorially it's not possible to put both of them in the one line. So I'm drawing this way. Both of them come into the same vertical line. And this vertical line has 50 and this vertical line has 70. So our output is the top nodes in every vertical line. So 30 comes here, 20 comes here, and then 10, and then 50, and then 70. Now this might be confusing that you have two nodes which are not falling into the same line, but we are considering them into the same vertical line. So it's always a good idea to follow the convention of horizontal distances. Horizontal distance of root is considered as 0. Horizontal distance of left child is considered as -1. So when we have distance HD for a node, distance for left child is HD -1, and horizontal distance for right child is HD +1. That's a simple rule we follow. So we have 0 for the root, -1 for the left child, and -2 for left of it, -1, -1. And -1 +1, 0 for the right child. Let's see the horizontal distance for this one. It's parent +1. So it's going to be +1 for this child. Now it has two children, and the left child is going to have +1, -1, which is 0. And the right child is going to have +1, +1, 2. When we go to the right child, we add 1. When we go to the left child, we subtract 1. So these are the horizontal distances. Now if we see how many nodes we have at horizontal distance -2, we have only one node. And how many nodes we have at horizontal distance -1, we have only one node. So when we have one node only, we can simply print those nodes. So 30 is the output for this vertical line, 20 is the output for this vertical line. Now let's see the horizontal distance 0. When you have multiple nodes at the same horizontal distance, for example, for 0 horizontal distance, we have 3 nodes. And that's why we are calling them into the same vertical line. In this case, we always need to print the top level node because we are printing the top view. Now, if there is a tie between two nodes are at the same level and both of them are the first nodes, then which node should be preferred? For example, this tree. You have two nodes here which are at same level, right? This is level 0, level 1, level 2, level 3, and level 4. So both of them are at level 4. And both of them have the same horizontal distance. You have 0, -1, 0, -1, -2, right? When we go to the left, we decrement. When we go to the right, we increment. So 0 + 1, then 0, then -1, then -2. Now, which of these two should be printed first? In such cases, we always give preference to the left child. Since this node has come through the left child of the root, we are going to give preference to this particular node. So that's why this node is printed first in this particular example. If we have single node in the tree, we need to print the single node. That's the only node in the top view. If our tree is empty, we do not need to print anything. If we have a tree structure like this, we can again compute horizontal distances. This is 0, this is -1, this is -1 + 1, 0, this is 1, and this is again 1. Right? It's better to compute horizontal distances than drawing the vertical lines. So we have one node at horizontal distance -1. So we print this node in the top view. Here we have two nodes. So we print the above level node. So we print 1. Here we again have two nodes. So we print the above level node. So we print 3. So that's the output expected from this tree. Now please pause this video and try to write down a program that takes a tree as an argument and prints top view of it. A hint for you is this problem is slight variation of the vertical traversal of binary tree problem. We only need to make minor changes into that solution and we will be able to print top view of binary tree. Let us now talk about the idea for implementation. We first build a map. A map is a key value pair where key is your horizontal distance and value is going to be top node at that horizontal distance. And maps are internally implemented using cell balancing binary search tree. A map is represented by map class in C++ and tree map in Java. So first thing we do is we do a level order traversal, and by doing the level order traversal, we build a map, right? We have -2, 30. So there's only one node at -2 distance, so it's going to be 30 for sure. From -1, we are going to have 20. But for 0, we have 3 nodes. So we are going to put 10, right? That's why we are doing level order traversal, so that the top level node comes first in the map, right? So 10 is pushed into the map. Then we come to the next horizontal distance 50, and we have 50 for horizontal distance 1. Once you build such a map, your task is to simply print content of this map. And since map is internally implemented using cell balancing binary search tree, we can simply traverse through the map and print the content of it. Please note that in Java, map is an interface which is implemented by both tree map and hash map. Hash map is not sorted, right? It does not maintain any order, but tree map maintains an order of the items. Now, how do we build this map using level order traversal? So we are going to use the same concept as vertical traversal. We are going to create a queue of pairs. So first we create a queue of pairs where the first entry is horizontal distance and the second entry is value. So this is our queue of pairs. Now we run a loop, a standard level order traversal loop, and inside this loop what we do is we take out an item from the queue and we process it, and then we enqueue its left and right children if they exist. So we take out this item. When we take out this item, we see that horizontal distance for this item is 0 and value is 10. And our initial map is empty. Map does not contain anything, right? So when you take out this item, you notice that at horizontal distance 0, we do not have anything into the map. We do a lookup into the map and we figure out there is nothing in the map for horizontal distance 0. So what we do is we push this value and this key into the map. An interesting observation here is in the top view, we are going to push a value into the map only when there is no value for the current horizontal distance. For example, if you see 0 again, you will be seeing 0 again when you see this node. But at that time, you will not be pushing this node. The reason is we only want to have the top level node into the map, right? That's the whole purpose of doing it. So the logic is simple. You do queue based level order traversal. When we do queue an item, at that point, see if there is already an entry for the given horizontal distance. If there is already an entry, then simply ignore this node. Otherwise, insert this node into the map. So you are going to always insert the first node in the level order traversal. That's how you are going to ensure that you have the top view of binary tree. So in this case, we did not have anything for horizontal distance 0. So we are going to put it into the map. So our map is going to contain 0, 10 as a pair. And now we are going to do normal level order traversal thing, that we are going to enqueue its children into the queue. And its children are 20 and 50. So we are going to enqueue 20 with horizontal distance -1 and 50 with horizontal distance as +1. This is our queue now. And after that, we do the next iteration of this loop. And in the next iteration, we take out an item. And this time we have horizontal distance as -1 and value as 20. Right? In every iteration, we take out an item from the queue in level order traversal. Now we do a lookup into the map. Do we have anything for -1? We do not have anything. So we are going to insert -1 and 20 also into the map. Right? And after that, we will do the normal level order traversal thing. We will enqueue its children. So we will enqueue 30 and 40 with their horizontal distances. So our queue is going to look like this now. 51, and then we'll have 30 -2, and then we'll have the next one, 40 and 0. Right, so this is what our queue is now. Now we'll again do the same thing. We'll take out the front item from the queue. So we'll take out 50 now. So when you take out 50, your horizontal distance is going to be 50. Your horizontal distance is going to be 1. And your value is going to be 50. So now you will do a lookup for 1 into the map, and you will notice that this 1 is not present into the map. So we are going to make an entry into the map for 150. And next thing we are going to do is we are going to process its children. We are going to enqueue its children. So our queue is going to look like this now. 50 is processed, it's removed from the queue. So we are going to have 30 -2, 40, 0, and then we are going to have 60, 0. So this is our queue now. And we'll do the same thing, we'll repeat the same thing in the level order traversal. We'll take out the front item of the queue. So this time you will take out 30 minus 2. So your HD will be minus 2 and value will be 30. And now you will do a lookup into the map again. Do we have anything for horizontal distance minus 2? See, if we have anything, we will not insert it because we want only the top level nodes. So we do not have anything for horizontal distance minus 2. So we are going to insert minus 2 and 30 into the map. See, I have written the insertion order, but map internally maintains the sorted order. So minus 2 will be first in the map, then minus 1, then 0, then 1. So this is what our map looks like now. So we have processed 30 minus 2. And now we are going to see if 30 minus 2 has any children. See, left and right for 30 and minus 30 minus 2 are null. Basically 30 are null. So we are not going to enqueue anything. Now our queue is going to have 40 and 60 only. So now we have 40 and 60 into the queue. We are going to do the next iteration of the level order traversal and we are going to extract 40, 0 from the queue. So HD is 0 now and value is 40. Now we'll see, do we have any entry into the map for HD 0? When we do a lookup, we find out we have an entry for HD 0. So what are we going to do? We are going to ignore this particular node because we already have seen a node which is above than this node with same horizontal distance. So this node is not going to be part of top view. So we ignore this node. And now we process its children. It does not have any children, both are null. So we do not enqueue anything. So our now queue contains 60 and 0 only. So we take out an item. Our HD is 0 again and value is 60. We again do a lookup for HD 0. We see that we already have an entry for HD 0. So what are we going to do? We are going to ignore this node also. So after this point, after you have extracted 60, 0, your queue becomes empty, your level order traversal ends, and your map has the required value. And again, this map is going to be a tree map in Java or map in C++, which maintains the sorted order of keys. So your map is going to have this order, and now if you print the map, you will get the required output. For implementation details of this problem, you may refer the vertical traversal video. Queue implementation is same. We have a queue of pair. Map implementation is even simpler in this problem. In vertical traversal, what we were doing, we were maintaining a map where integer was a queue and value was a vector in C++ and array list in Java. Here, our value is also integer because we are going to have only one node for a horizontal distance. So implementation is very much similar to vertical traversal. There, we were pushing every node into the vector or array list for a given horizontal distance. Here, we are going to do a lookup for this horizontal distance in the map. If it already exists, we are going to ignore it. Otherwise, we are simply going to put single value for every horizontal distance.